Okay, so this is going to end up being like 2 videos. But that's okay. So I'm definitely too lazy to put the 2 videos together into one video. I'll just upload 2 videos much quicker. All right, so we were doing an example of second derivative test. You can look at it there if you want while I get myself in order. There we go. Okay. All right, so we have 10 minutes. What I want to do is introduce you to optimization. Okay, this is going to be the main focus of when we get back from spring break. Okay, what is this, section 4.7, I think? So let's look at an example. Let's say that you have some fence, and let's say you're a farmer or a gardener. You've got some fence. You have like 100 meters of wire fence, and you want to build an enclosure for animals or garden or something. If you use a barn as one side of that enclosure, so that side does not require fence, and use the fence for the other 3 sides. Question is, what is the largest, what dimensions, I guess? Oopsie daisy. What dimensions will produce the largest area? Okay, this is a question of optimization given some scenario. How do we optimize it? Okay, let's do some steps. First of all, I want to draw a diagram, a lot like how we start off with a related rates problem. I think once I came up with like a kind of a weak, sort of half-assed acronym. Doesn't spell anything good, like dreads. But there's a sort of a process similar to dreads that you can go through to figure out, to do an optimization problem. So first we'll draw a diagram. So here's the barn. Okay, so we're just going to assume that the barn is nice and long, and we don't have to worry about running into the end of the barn. So the wall of the barn is like one side of the enclosure, and then the other 3 sides of the enclosure are going to be fence. And I probably forgot to say, but this is going to be a rectangular enclosure. A rectangular enclosure. There we go. Okay, so the entire length of the fence, like the total length, can be up to 100 meters. And I think it's obvious that if we want to maximize the area inside of this enclosure, we want to go ahead and use all 100 meters. So we're going to have the total length equals 100 meters. Now, we could build it like this, or we could make it like that, or we could make it like that, right? There's sort of like different shapes that you could make, right? Having either be like long and skinny, or maybe like a perfect square, or maybe like you want it to be like super thin and like stick way out, you know, like that. These are all different possible shapes that you can make with your 100 meters. Does that make sense? So there are two, if I focus back in on this one, there are two variables here, okay? There's like this one, which is X, and there's this one, which I'll call Y. X and Y are just two random letters that I picked, right? The X and Y are going to be two variables. Since there's two X's and one Y, if I add them all together, 2X plus Y has to equal 100. Okay. And this information right here, this information is called our constraint. Okay, that's our constraint right there. A constraint is a piece of information that basically puts a limit on the values of the variables involved in this problem. Like so it's the constraint essentially is a rule that those variables have to follow. And so our constraint is that we have, and we're going to use exactly 100 meters of fence to form this enclosure. Okay. But the constraint is not the thing we want to optimize. The thing to optimize, which I wish I had a better name for it. You can help me think of a good name for that. What is the thing to optimize? The thing to optimize in this case is the area. And the area, we can also calculate the area using our variables. What is the area as in terms of like X and Y? Excuse me. You guys remember how to do area of a rectangle? Not getting much feedback here. Here we go. Yeah, here it comes. All right, now here it came in the chat. I wonder if I had a little bit of a lag there. Length times width. Yes, area is going to be X times Y, X times Y. Yes, that's correct. That's right. Just X times Y. Great. So what I want to do to optimize my area, I need to get the area in terms of like a single variable. Because what we've been doing with our optimization, or with our like finding local extremes and stuff over here, it all relies on having a function of one variable, right? Like f of x, it's one variable. So right now I have two variables problem, but with the constraint, I can make a substitution which and that substitution will bring me down from having two variables in the formula to having only one variable in the formula. This is the same concept as like solving a system of equations, right? If you have two equations involving x and y, you can solve one of them for, say, y, substitute it into the other equation, and now that equation will only involve an x. That's what we're going to see here. So my area equation is now x times 100 minus 2x, right? So this is using the constraint to simplify the function that you need to optimize, right? Now this, if I do a little algebra here, it's like negative 2x squared plus 100x. Now this is a function I can differentiate, negative 4x plus 100. I can find critical numbers, a prime equals 0, when Negative 4x equals 100, or sorry, negative 4x plus 100 equals 0. So like 4x equals 100. So x equals 25. Okay. A prime undefined, never, thankfully, because it's a polynomial. Okay, so there we go. There's my critical number. And then I can use an extreme, like a test for extreme value test of some kind. So don't forget to use an extreme value test. Just because you found a critical number doesn't mean that it's the right type of critical number. We obviously want to maximize the area. If you accidentally found a critical number that minimizes the area, that is the opposite of what you're looking for. So don't forget to check that the critical number you found is the right type of extreme value. So for that, we need one of these tests. So I'm going to just use the second derivative test here. Since a double prime at 25 is equal to negative 4, which is negative, A has a local maximum at x equals 25. Okay, our second derivative is a constant, which is nice. It's always negative 4. Okay. So there we go. So now there was a theorem a little while ago I showed you that said that if there's only one critical number and it's a local extreme, it's also an absolute extreme. So this is also the absolute maximum. So we can say max area is when x equals 25 meters, and y, we can solve for y by going back into our constraint. If 2x plus y has to add up to 100 and x is 25, 2 times 25 is 50, y has to be 50 as well. And that is the answer to our optimization problem. It's 25 by 50. Okay. And that's your first exposure to optimization. Folks, have a lovely week. I will see you when you get back, and we'll practice more of this.